Now to the solid state. Amorphous solids do not have a well-ordered molecular structure, a short-range order at most. Examples are charcoal, rubber, asphalt, and glass. Glass is an amorphous form of silicate. The molecular structure of glass is not well ordered, unlike crystalline silicate or quartz. Crystalline solids have well-defined structures that consist of repeating units called unit cells. Unit cells have lattice points. Atoms or ions occupy the lattice points in a crystalline solid. The crystal lattice consists of all points with identical surroundings. The coordination number of a particle is the number of nearest neighbors surrounding it. Crystals display X-ray diffraction patterns. As X-rays pass through crystals, the beam is diffracted to form a pattern. This pattern allows for the analysis of the properties of the crystal lattice. Studies indicate that 7 crystal systems and 14 types of unit cells occur. These crystal systems are cubic, tetragonal, orthorhombic, trigonal, hexagonal, monoclinic, and triclinic. Of the 7 crystal systems, I will mainly talk about the cubic system. Majority of metals, some covalent compounds, and many ionic compounds occur as cubic lattices. There are 3 types of cubic lattices. The first one is simple or primitive cubic cell. Here, the centers of 8 identical particles form the corners of a cube. Assuming there is only one type of particle, the coordination number here is 6. The next type is body-centered cubic cell, wherein identical particles lie at each corner and in the center of the cube. The coordination number for a system with one type of particle is 8. Face-centered cubic cell has identical particles lying at each corner and in the center of each face, but not in the center of the cube. This is also called cubic closest packing. Coordination number in this case is 12. Here again are the particles packed according to the 3 types of cubic cells. In principle, only portions of particles positioned at the corners and the sides form part of the unit cell. Each corner is occupied by only 1/8 of the particle. And if we are to combine all of these particles together, it will result to 1 atom per unit cell. Simple cubic cells are not very efficient in terms of packing. It only has 52% packing efficiency. If we are to determine the radius of the particle, we can just take the length of one side, and taking note that each side is 2r, or twice the radius, the radius can be easily calculated. For body-centered cubic, the packing efficiency increased to 68%. If we take the one whole atom in the middle and the 1/8 of the particle on each side, there will be 2 atoms per unit cell. To determine the radius of the particle, we need to use Pythagorean theorem. If the length of the side is known, then b can be determined. b squared is equals to 2a squared. Then c squared can be calculated. C is equal to 4r. Hence, a is equals to 4r over square root of 3. Face-centered cubic has the highest packing efficiency of the three, around 74%. There are 4 atoms per unit cells. The 3 atoms comes from the atoms on the side of each faces, and the 4th atom comes from the combination of the 1/8 particles on each corner. If the length of the side is known, then we can easily determine the length of the diagonal of one face by Pythagorean theorem. If b is equals to 4r, then b squared is equals to 16r squared. Hence, a is equals to the square root of 8r. Exercise 6. Copper has the most essential industrial application of the 3 coinage metals. Its crystal structure adapts cubic closest packing, and the edge length of the unit cell is 361.5 picometers. What is the atomic radius of copper? Given that copper has a cubic closest packing, then we can use the formula given in the previous slide. A is equals to square root of 8r. Rearranging the equation will result in r being equal to a over square root of 8, which gives the radius equal to 127.8 picometers. In atomic solids, individual atoms are held together by dispersion forces, for example, noble gases. Frozen argon exists in face-centered cubic unit cells. In molecular solids, the lattice points are occupied by individual molecules, which are held by various intermolecular forces. For example, in this case here, methane and water. Methane exists in face-centered cubic unit cells. In ionic solids, unit cell has cations surrounded by as many anions as possible, and vice versa. It has the same cation to anion ratio as the empirical formula. Shown here is the crystal structure of sodium chloride, exhibiting a face-centered cubic unit cell. Sodium and chlorine are present in this unit cell in 1:1 ratio. In metallic solids, powerful metallic bonding forces hold individual atoms together. They have high electrical and thermal conductivity, luster, and malleability. In network covalent solids, covalent bonds link the atoms together. Because the atoms are connected by covalent bonds, They have extremely high melting and boiling points. Examples of network covalent solids are graphite, diamond, and silicates like quartz. In summary, here are different types of crystalline solids. We have the atomic solids. They are soft with very low melting points and poor thermal and electrical conductivity. We have molecular solids. They are fairly soft, low to moderate melting points, poor thermal and electrical conductivity. Ionic solids, held by ion-ion attraction, since they are hard and brittle, have high melting points, have good thermal and electrical conductivity when they are molten. Next are metallic solids. They are held by metallic bonds. They are soft to hard, have low to very high melting points, have excellent thermal and electrical conductivity. They are malleable and ductile. Lastly, we have network covalent solids. They are held by covalent bonds. They are very hard. They have very high melting points and usually poor thermal and electrical conductivity. Examples for each case are also provided.